Good morning, all. I am Karthik Reddy, a research scholar. Welcome you all for the day 3 session 2 of a NAMPET sponsored short-term online course on power electronics converters applications in microgrid and vehicular technology from 20th July to 24th July 2022. Organized by the Department of Electrical Engineering, National Institute of Technology, Rourkela, Odisha, India. It's an honor and privilege to read the biodata of Professor S.P. Singh, sir. Professor S.P. Singh, sir, received a PhD in electrical engineering from IIT Rourkela in 1994. He worked as a scientist B at Alternate Hydro Center, University of Rourkela from 1983 to 2001. He has nearly 22 years of teaching experience and currently working as a professor at the Department of Electrical Engineering, Indian Institute of Technology. He is an honorary member in IEEE, a fellow in the Institution of Engineers India, and a life member in IAQR. He has been awarded with Khosla Research Award in 1990, REC Chair in 2014. He published about 69 research papers in various reputed international journals and 128 in national and international conferences. Under his supervision, about 17 students were awarded with a PhD degree and 2 are under submission. He has been associated with various projects and prepared detailed projects reports of small hydro projects and condenser discharge of thermal power plants sponsored by various organizations like NTPC, MNES, IREDA, CanMet Canada. Under these, few projects are super thermal power projects at Singrauli, Korba, Faraka, etc. And he has prepared detailed projects reports of 35 small hydel projects of Arunachal Pradesh, Mizoram, Jammu and Kashmir, Tripura, and private developers of some states in Darjeeling area, sponsored by Department of Power of various states, agencies sponsored by MNES. His research interest includes diversifying ideas like hydel, wind and thermal power generation, power apparatus and electric drives, fax devices, power quality improvement, power electronic converters for renewable energy systems, etc. I welcome you, sir, once again for the talk. Over to you, sir. Thank you.
Thank you, Mr. Karthik.
Thank you, sir.
As such, I have started a career as a scientist in Alternate Hydro Energy Center, and the aim of the project was let me close. The aim of the project was to develop the hydropower stations in remote areas using unconventional technique. Normally, what we do when we generate a power. So as such, nowadays we are the basic principle remains same. We are going through the same process. Once we are going to generate a power, so the basic requirement, our basic requirement, how we generate a power. So there are the different resources like hydro, wind, and thermal. So initially, we started with the hydro and thermal power plant. So the basic components of the hydro and thermal plants are like a governor and exciters, the exciters, other than the mechanical the components and the electrical components. So basically, these are the two things, main components are, yes, the main components are, say, governors, the mechanical governors, and the exciters for the generators and the governors for the turbine. So the function of the two components, the basic controllers is to control the voltage and the frequency. So anyway, in any case, whatever be the method of the power generation, we have to control the voltage and frequency. So then a situation comes, how we are going to operate our system, whether they are interconnected or in a standalone mode.
Hello.
Okay, so the function, the functions of the governor and the excitation systems are say regulated in different way. Let me take an example when we are working in an interconnected system. So the function of the exciter is to not only the maintain the voltage regulation, to share the reactive power between the generators, and they must share the power proportional to their power rating. And the function of the governor is to say control the frequency or regulate the frequency at a fixed level, and depending upon the size of the machine, so some machine, the larger machine, can be used for regulating either voltage and the frequency, or the other machines work in other other machine work in a as a constant input power, or a constant power factor mode. So the basic concept remains same, and nowadays we are going to harness the renewable energy sources like PV and wind and all that, so we cannot have the conventional controller. So in those days, we developed the controllers, say for standalone generators like induction generators, synchronous generator, and how we can control the voltage and the frequency of a.
Sir, good morning, sir. SP Singh, sir.
Yes, sir. Yes, please.
Hello.
Yes.
Sir, your screen is not visible, sir.
My screen is not visible.
Yes, sir. For me, I don't know for others.
Yes, sir.
Good morning, sir.
Good morning. Good morning.
It's not visible.
Not visible, enough.
Yes, sir.
Yes, yes, sir. Please share your screen, sir. So, sir, on the top of the bar, you can able to find the screen arrow bar.
Yes, yes.
No, I know that. I know that. Please, wait
Sir,
for some time.
Okay.
Wait. Okay. And now tell me, is it visible now?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir. It's visible, sir.
So by this time, I have not opened the file. Okay. So the basic remains, how to control the voltage and frequency in case of standalone or the interconnected systems. So we did develop say different controllers, say for controlling the voltage and the frequency of synchronous generator, induction generator. Okay, so these are the basic, the fundamentals, how we going to control the voltage and the frequency, in any system. So when we are going to develop you can say the renewable energy sources like wind, hydropower, small hydro particularly, or photovoltaic system, we cannot use the conventional control. It is not possible. Okay, so that is why. So at that time we tried, say for small hydro, say how we can develop the load control in case of the inflow controller. We control the output. By controlling the output, we can maintain the voltage and frequency. Whatever the generator may be, the different techniques are available and different options are available with us. So nowadays the situations are changing. So let me take an example of the photovoltaic system. So the power available is in the form of the DC, and then we need a converter. So the converter, then converter may be say DC to DC converter, DC to AC converter, and depending upon the load, they can connect it to the isolated load, or they may be connected to the interconnected system, or they can be connected in parallel, say to make a mini or say micro DC grid or AC grid. So now questions come in, how we are going to control these inverters, So nowadays a lot of research is going on how to emulate the operation of the inverter or the converter, any converter in a parallel operation, particularly inverters, how we how we must share the power depending upon the input, and as well as to regulate the voltage or share the power proportional to the power generation. So as such, the we have nowadays we are say working this area nowadays, hardly there may be some grid. I think in India there is no grid available, macro or mini grid is available of DC. Nowadays, we are trying and we are doing research in this area how we can generate a localized grid and 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 emulate the operation of the inverters like a to control the voltage and frequency like a governor and the excitation the exciter, how we use. Nevertheless, we are going to discuss the power the what kind of the power converters we are going to use, say for electric vehicles and the plug-in electrical vehicle. So because of the lot of pollution is there everywhere, so we have to switch over, say, from conventional vehicles to uh, the electrically operated electrical or the EVs and PAVs. So let me say begin with this, what is a BEV and PHV. So just see, this is a short form. BEV is a battery electric vehicle, and there are certain companies making these vehicles. And PHEV is a plug-in electric vehicle, and say PHEV is plug-in hybrid electrical. As such, there are the two sources, more than one sources input sources there to drive the vehicle. So hybrid means it can has battery or the normal petrol or diesel engine, and here you can see the examples. The different companies are making such vehicles. So Mitsubishi, Volvo, BM, so many companies are available. So basically, when we are dealing with the converter, so now, so in this lecture, I am going to say have a look on the available converters which may be used for the electric vehicle applications. So what we are supposed to do now, we have to charge the battery. So say then how to decide a charger or the topology of charge, and it will depend on where you are going to charge and how fast we are going to charge the battery of the vehicle. And so there are the different categories of the charging. So one is a trickle charge, AC charge, and DC charge. So this is the lowest, the speed, this is the slowest method for charging electric vehicle, and we can use a standard 220 volt plug, and this is only recommended when the urgency is required. And AC charge, having a ball box installed set, so this is 3 to 4 times charger than the household charging method. And the AC public charges, so we use for this purpose, we use the DC charge. So this is the fastest way to charge a battery, and say, so we can charge a battery up to 50 kilowatt and above. And and you can say you can charge the battery fully from 20 to 80% in approximately few minutes. Oh, Okay, and there are some charges up to 150 kilowatt capacity are available. Okay, and typical charge method. So this is the simplest method, and it is not required every time, and it can say take charging range and say maybe 30 to 60 kilometer per hour charging, and charging speed is very slow, and this is recommended only in the urgent cases when you have to when you have a low battery charge and you cannot drive your vehicle up to the public charging station. So in that case, typical charges uh, charge method can be used, and you can use it in your at your home also. And then there is another AC household charging method. So this is a little bit faster, and this you can this charges work at a 230 volt and faster 3 to 4 times than the typical charge method. And you can use your say this method for charging a vehicle overnight. In overnight, so the battery can be charged, and this may be the ideal if you have a garage. If you have a garage, you can put your vehicle in the garage and you can use such chargers, and within overnight your vehicle will be fully charged. And then the public charging stations. So in this case, normally DC charger are used. So there is a system, another AC is available, then AC is converted into the DC, and DC is used for fast charging, and it can charge 3 to 10 times faster than the household charging. Then comes the fast charger. So this is data on some fast chargers. They are able to charge 20 to 80%, from 20 to 80% capacity of a battery within 40 minutes. Okay, and then we can have a comparison AC versus DC charging. So you can go through this AC charger. They are the EVs onboard chargers, which converts AC to DC, allowing the battery to charge. Okay. So there is a problem with the space. Because of this space, the capacity of this charger is very small. So as such, for onboard charging, so the complete system is inside the vehicle, and because of that reason, so the charging is very slower. In case of the DC fast charger, your charging system is external to the car. That is why these chargers are very fast. Size becomes say large, and they so no need to explain this slide. Okay, so hybrid vehicle. This is regarding the hybrid vehicles. This is a combination of the electrical and mechanical component. So here we can have a look. They are the main sources of electricity for hybrid vehicles, like fuel cells and the supercapacitors. So each device has the low cell voltage and has required many cells in series to obtain the voltage divided by hybrid electrical vehicle. So here we can find out the difference between the different sources required for the battery or the electric vehicles. So three possibilities are there. We can have a fuel cell, battery, and the capacitors. Okay. So here you can note down the limitations, and if we provide the high energy but low power. Battery supplies modest power and energy, and the capacitor supplies very large power but low in energy. So this is the basic structure, and you can see. So this is the bus and AC supply. So and this is the your vehicle system, public vehicle system. Here you can see the onboard charge. Onboard charge, onboard charge, and this is a portable bed. This is a battery. So you can charge this battery by the onboard charge or fast charging method. Both way it is possible. And the onboard charge, they are inside the vehicle, and because of the space problem, so the charging with the onboard method is very slow. Then comes a DC to DC converter or DC, and the other source may be the super capacitors. Okay, and then from the super capacitor, output of the super capacitor, so there is a DC to DC converter, and here is the DC bus, high voltage DC bus. And from the high voltage DC bus, so there may be, depending upon the type of the vehicle, so there may be 3-phase inverter to drive induction machines, or the other may be, or in case the power is sufficiently available, then we can again recharge the auxiliary battery by connecting low voltage DC converter or the buck converter. So this is a typical structure of the electric vehicle. And here now let me discuss the issues with the electric vehicles and the PHVs. So normally the power from from the sources to VEB and PHEV is unregulated. Battery and supercapacitors face voltage drop during the and in case of the fuel cell, dynamic response during the transition causes the high voltage drop in slow time. So this is the limitations of the fuel cell. So some as such, this is not common in use, say in electric vehicle because of this limitation. And fuel cells, faces other problem like the infrastructure is costly and this is not available everywhere. Supercapacitors are suitable for capturing energy during the braking and deliver the instantaneous power for acceleration and deceleration. So as such, here the advantage with the supercapacitor, when you want to accelerate the power or accelerate, so you can use you can make a use of both sources like battery and the supercapacitor, and because of these combined sources, you can accelerate, and during the deceleration, the converter can maybe work in buck converter can be used for say storing the energy in a battery or for the braking operation. So the idea is when you are say decelerating or applying a brake, so you must be able to absorb or store the kinetic energy in a battery. Okay. And there is another advantage, merging SC with the battery reduces the stress on the battery. And say for bidirectional sources battery and supercapacitor, they are the bidirectional sources. So the bidirectional converters are necessary to absorb the regenerative energy. And say for fast charging and discharging capacity of the super capacitors. So what is the requirement for fast charging and the fast discharging? So one must design a controller with the fast dynamic response. And with FE as a resource, DC-DC converter with a small passive element is necessary to lessen the interval between charging and discharging mode. Okay, so this is important, the size of the passive element. Why the size of the passive element placed in a converter should be small. Okay, so this is the region. So as well as to reduce the interval between charging and the discharging period. So in case of the battery, fast dynamic control is not required. As in case of the battery, it is not required. It can say last for 30 minutes. So this point we have already discussed, and in case of the battery for dynamic control is not okay. So these are repeated. Say common characteristic of DC-DC converter. So when we are designing a DC-DC converter, we have to keep in mind the voltage gain must be high. Okay, and then it must be capable to deliver the power over a wide range of the voltage. That is the requirement of your converter. And high voltage DC-DC converter, they are required to increase the unregulated DC source to a highly regulated level by transitory storing the source of energy. It means that the source of energy normally they are available at low voltage level. So that means that you need a high voltage DC-DC converter. Say to maintain a constant voltage at a DC bus. So the advantage of DC-DC converter over a AC DC converter, they are light in weight, compact size, low priced, highly efficient and reliable. DC-DC converter can be regulated spontaneously. That is the advantage during the rush driving. Disadvantage of a DC converter. So the voltage gain is very small or very moderate. Okay, and they are unable to attain a high power density, and there may be low efficiency because of the hard switching. Nowadays we are having a converter with the soft switching, the efficiency can be improved. And the main problem is here. So people normally do not work in this area. That is the control. What does it mean? What does it mean of this statement? It is very hard to design a robust high bandwidth control loop due to the presence of the right half plane zero in the transfer function. Why this characteristic is there? This is because of, say, high order filters are available at the output. Normally, in case of the normally, say, boost converter, buck converter, that is the we can have it as RC elements or RLC element. So when the order of the system becomes more than two or more than two, it becomes very difficult to stabilize, and for that purpose, we need a controller. Okay, so normally, so this is the important research area. Too robust high bandwidth, so your converter or your voltage must be stable for any change in the input or change in the output, say for a wide variation in the operating frequency range. So let me give you some idea, and for that purpose, you can say refer the Power Electronics book by Abraham Pressman. So you can note down the Abraham Pressman. So this is a very old book, and you can go through this book, and there may be chapter 8. I think there may be chapter, you can go through, there may be chapter 8, something like that, how to design a compensator. How to design compensator. It means, how to stabilize the feedback loop. Okay, feedback loop. This is important, and when we stabilize this feedback loop, so in that case, we select or say we design a PI control. Normally we design a PI controller, and how to get this value of P and I controller, and then so once we get these value, then how to realize this controller. Realize the controller. So in that case, in controller, you have to calculate the parameters of the controllers. Like resistance and the capacitances, along with FHN, we are using error amplifier. So once we are designing an error amplifier, so what is the function of the error amplifier? Okay, so it controls the pulse width to the gate devices. Okay, and as such, the pulse width is decided by, it is affected by the load on the converter or any change in the input, and in order to stabilize its operation for a high bandwidth, so we have to select the suitable value of R1 and these controller parameters. So meanwhile, what you can do, let me okay, and just see. So you can go through this book, and here you must be able to the basic fundamentals. What are the problems with it when we are designing a converter? What are the fundamentals? Why the system becomes unstable? So this is the second order system circuit, at the output of the converter, and here simply I just give you the idea why the system and a second order system becomes unstable. Say So here you can see the gain versus the frequency curve. So depending upon the damping ratio of the system, say for critical, there are the three possibilities. The system may be critically damped, or the under damped, or over damped. So the response is, say for under damped, the response is like this. So here you can see the crossover frequency. So here the main problem is, in case of the second order system, when the gain is when the order is 2 or more than 2, their slope is minus 40 dB per decade. 40 dB per decade or more than that. Okay. So here you can see the gain behavior. Here is the phase behavior of the second order system. Phase behavior. So what happens, say in case of the underdamped system, the phase, just see, so the phase of the converter changes very rapidly. So here, simply you can go through the book, that book, I am giving you the idea, and I am telling the fundamentals. What is the problem? Critically damped circuit has a very small bump. At a corner frequency. This is a corner frequency. Underdamped circuit has a very high resonant bump. So this is an underdamped system. Okay. And overdamped system, so in case of the overdamped system, so the gain approaches asymptotically minus 2. So as such, here for a overdamped system, so there is a drop in the gain 20 dB, 40 dB to 40 dB per decade. 40 dB minus 2 slope means 40 dB per decade. Okay. So here in this case, so the slope, the and corresponding to this. Okay. So here another second order system. Suppose we are having a system whose gain slope is minus 2 at crossover frequency. So the change in the phase, say what 20 times at the corner frequency. It means with a slight change in the frequency, so the phase may be more than 180 degree. Okay, so in that case, once you have a change, with a slight change in the frequency, little higher than the crossover frequency, and say and this frequency is say 1.5 times, say 1.5 times of the crossover frequency, at a frequency which is 1.5 times the crossover frequency, the phase reaches something around more than roughly 170 degree or 180 degree, and little more than that, so here you can see again the phase shift is 180 degree. Okay, so as such, we have to save this. The phase. If we are not able to save this phase, what will happen? The system becomes really unstable. Now, these are the basics you must understand how to make the system say stable. So that is the region, you know. So say from the research point of view, na, so you pick up any topology and model the topology and see this response, you know. So everything is okay as long as it is working in an open loop, and the closed loop operation is desirable. This is very much desirable, and until unless that you are not getting the proper closed loop open uh, uh, loop response, you know, so your device may not exactly, it will not work in the field. So that, you know, you have to keep in mind, you know. And as such, you know, here you see this line is important, you know. A circuit with a -1 gain slope will never yield a phase delay by 90 degree. Okay, so a system with -2 slope and it achieves a gain of 180 degree at around, or little more more than the crossover frequency. And if you are having a circuit, if you are having a circuit with -1 gain, or slope is 20 dB per decade at a crossover frequency, so the maximum phase system phase delay, or the phase delay is 90 degree. It means, you know, so only how much phase shift we can afford? We can afford a 180 degrees phase shift. 180-degree phase shift, you know, because of the error amplifier. This is because of the error amplifier. It is always there. And the balance remains 100-degree system. And suppose, and that may be because of the converter, the system converter, the circuit. And suppose, okay, and total phase, is 180 plus 180 means 360 degree. When your phase shift is 360 degree, it means your negative feedback system becomes positive feedback, and the system becomes continuously, this becomes unstable. So that is why we cannot afford to have a system which is having -2 dB, -102 slope, or -40 dB per decade. So as such, we have to design a compensator, or additional, we have to design a compensator which will which is combined with the circuit or the filter, and that gives this much gain. So here, you can understand so how the system can be made stable. So the first criteria, so the total phase shift at a crossover frequency. What is the crossover frequency? Frequency where the total open loop gain is unity or 0 dB, and that should be sort of 360 degree. By the phase margin, normally we take 45 degree, 60, or even 45 is okay. That is the first criteria. The second criteria for the stable system is to prevent a rapid change in the phase shift of frequency, characteristic of a circuit with -2 gain slope. So therefore, the open loop gain frequency curve of the entire circuit, it should pass through the -1 gain slope. So what I mean to say is, say suppose suppose your slope at crossover frequency is -2. So the phase shift is very rapid. Phase shift is rapid, and this is a normalized frequency, and this is the phase shift. Phase shift is very rapid. Just the phase shift, so here the phase shift is very rapid. And suppose I take suppose I take total open loop gain whose slope is -1. So the phase shift must be like this. With the change in the frequency, here you can just change in the frequency. So this frequency curve phase shift increases slowly. So that is the second criteria. And the third criteria for the stable loop is to provide a desired phase margin. So that is there. So for this purpose, you can read Abraham Pressman or any Abraham Press book, or there are many other books available to design a second order or the third order system, third order or the fourth order system. Okay, so this is a very difficult task. You must understand. This is a very complicated, and you have to understand the complete. This is very design is complicated. Okay, so you have to understand why the stability issues are important. For the design of converters, any converters. So as such, what normally people do, they pick up P and I value randomly and pick up a fixed load, and they try to stabilize the system. So that is not a correct approach. We must have it. So theoretically, we must have the simulation. Theoretically, we must first design these values and then validate with experiment. So let me again switch over to so that is why this is very important. Very important. Suppose somebody works on this, and design the controller properly, so his or her thesis will be through, and he will publish, and verify etc. And he is able to validate the design of the controllers. And so nowadays, and what we are there, nowadays what we are doing, and we are say working in this area, wide band gap, wide band gap silicon devices. So here, so advantage with the WBGS technology is that so we can achieve a higher power density. So these are say silicon carbides or the gallium nitrides, such materials are available. So the idea is we are in future we are going to use silicon carbide or the gallium nitride as a semiconductor device, semiconductor switching devices. so as to reduce the size of the converter for at a higher power rating. So the higher power rating is issue. Higher power rating for charging a electric vehicle. And now a lot of research, another research is going on modeling a new converter topology, a design a novel control loop concept for high power applications. These are the stability issues. We have to deal with the stability issues. And what kind of the criteria we have to look for while designing topology. So the size of the topology must be small. It must be reliable, parameterized, lightweight, controllable, scalable, and efficient as a height. And the answer topology is a full boost converter. So this can be selected for electric vehicles if galvanic isolation is required. So the galvanic isolation is important from the control point of view. Multi-phase, multi-port, or the multi-device boost converter topologies, which connect the multiple sources in parallel with the interleaving control to supply the power to the electric vehicle. And topologies that can minimize the input current. Okay, so why this is important? So the larger the ripple current, the smaller the battery life. So okay, and high bandwidth control, this is desirable as I have already discussed, and integrate. Okay. And basic issues are the number of charging stations and the charging time. When we're designing a converter, so the charging time and the number of charging stations, these are the main issues while designing a converter. So let us discuss the charging type. Charging type 1. So in USA, this works at 120 volt. In European Union, it operates at 230 volt. Type 2 chargers, so they are recommended for the public site. So they work at 240 volt in US and 400 volt in the European Union. And third commercial, the battery chargers, so they are known as fast charger. It means they can charge the battery up to 100% capacity within 30 minutes or half an hour, and the size of the battery may be 25 kilowatt hours. And such chargers are as of now available. So they are the two kind of the design. They are the two type of the fast chargers. So one is having common AC bus architecture. The second one is a common DC bus architecture. Common AC bus and different topologies are available for these architectures. So we have to decide these topologies on the basis of the number of components, ease of control, and the isolation, okay, and efficiency. So these are the different criteria: component count and ease of control, isolation, and efficiency. On this basis, the topology must be selected. So at present DC-DC converters, you know, for say for electric vehicles, so SI topology, you know, semi silicon topologies. SI topology, SI material is in use, and with this, you know, you can get the efficiency of 90 to 93%, and the allowable switching frequency is 30 kilohertz. This is the maximum switching frequency you can use. And here is the limitation: power density. Power density is a limitation, and you cannot use as such, and it is very difficult. The size becomes large. Suppose I use SI based the devices, you know, like MOSFET, not MOSFET, IGBTs. So high power, so these are the limitations, you know. And as such, you know, with the wide band gap, say WBGS materials, so we can achieve a capacity of 50 watt per inch cube. And such materials are, so the other gallium nitride semiconductors, or the other is gallium nitride, or the other is, I will let you know. So gallium nitride, you know, they are available in the market, and say for commercial use, and they can use, say, for the capacity less than 5 kilowatt with the 600 volt breakdown voltage, and the more test is being carried out on this material, on pure semiconductor material. So the idea is, you know, so lot of research is to be done on the semiconductor materials. Semiconductor materials for large, say for high power converters. Converters that can have the reduced size. So this is the data on this wideband gap silicon, the wide band of silicon material, wideband GaN. So this is the data. So this can have the efficiency of 40 watt per inch cube. So these are the different topology, you know, they can be used for electric vehicles, DC-DC converters, interleaved four-phase boost DC-DC converter, boost DC-DC converter resonant, you know, with resonant circuits, full bridge boost converter, isolated ZBS DC-DC converter, sinusoidal amplitude, high voltage converter, multi-board and multi-device bidirectional DC-DC converter. So here now you can have a look of DC-DC converter. So there are the two categories. One is non-isolated DC-DC converter. The other categories are of isolated DC-DC converters. So here you can see the symbols, you know. So the are the converters, non-isolated converters. So the and they are shown with the green symbol, green, you know. So here you can see this category, non-isolated converters like interleaved converters, multi-device or multi-port converter, and the boost converter. They are suitable for the electrical vehicles, battery operated electric vehicles or plug-in hybrid electric vehicle. On the other hand, so this is the list for isolated DC-DC converter, and here you can see these topology like bridge converter, jet source, FAHBC, multiport, and full bridge converter, not half bridge. So there are the two categories, full bridge converter. So again, these are suitable. They are found to be suitable for the electric vehicles or hybrid electric vehicles, plug-in hybrid vehicles. So just have a look at the non-isolated DC-DC converter. So they are suitable for the medium and the higher power application. And conventional boost DC-DC converter and interleaved boost converters. Normally they can be used boost DC. So here you can see the limitation of boost DC-DC converter. So the gain is limited to 4%. For low level DC voltage gain, two type of converters. Say if the requirement is, so your gain is less than 4 amp. So you can use such converters, boost converter, boost converter, cut converters, circuit converters. And out of these converters, only boost converter has the positive gain, which is required for the metering action. And if it's less than positive gain, and in that case, the only boost converter, they cannot be used for charging the battery. Buck boost converter, they can be used as a step down when the braking action is or the energy storage required. And for the voltage step up and a step down, where input need battery. When your supply source is either this may be battery or the supercapacitor. Okay, in that case, we are talking the source. When this voltage, when the energy source to the vehicle is battery or supercapacitor, so you can say up for the step up or the step downs. Okay, and they are the step up and step down converters, and they are like the current voltage and current type converters and suitable for the energy storage. Okay, and the buck boost converter, they are inconvenient for the automotive applications because of the high end current at the output, and which requires a large filter. And because of this, the size of the converter becomes large. When the gain is more than 4%, okay, so you have to say boost the input voltage from the energy source to maintain a desired level voltage at the DC bus in the vehicle or the electric vehicle system. So in that case, 4-phase interleaved boost converter is recommended. Isolated DC-DC converter, they are the loading. Okay, this I have already discussed. Isolated DC-DC converter, DC-DC converter. Low and medium power applications. Bridge topology more popular and frequently used for the half bridge, full bridge, push pull. So we are not going, normally we are going to full bridge converter. Isolated DC-DC converter has a three primary stages, say one DC, AC, and then DC, and AC, and then DC. And this topology AC, required to step up the voltage with a high frequency transformer. And this high frequency transformer provide the galvanic isolation and high voltage gain, which are the significant issues in case of the VEV and PHV. And there is another Z source as a single source, boosting AC DC suitable for the smooth starting operation but limited boosting capability during the zero vectors. So during zero vectors operation, so the boosting capability is limited. In this case of the Z source, single stage boosting DC-AC converters. Sinusoidal amplitude, voltage high converter. So these are the advantages, These are the advantages with the SA-HBC converters having low DVDT, DIDT, and with minimal switching losses. And the isolate MPC is most suited that minimize the input current and the output voltage ripples. So the MPC topology, this is most suitable because we have to minimize the input current as well as the input current ripples and the output voltage ripples. And the size of the component and the passive component is okay, and one can get the higher efficiency with high handling power capability. Okay, so DC-DC converter. So this is simply, so here there is simply DC-DC converter. So basically, fundamental converters are say DC buck converter, boost converter, and buck boost converter. Buck converter, boost converters, and then buck boost converter. These are the basic converter, basic topology. And out of these topology, higher topologies are derived. So how can I say as such this is the energy storing element. So the energy storing element decide how a converter can work. So you can place this energy storing element either towards the source side or the load side or between source and load. So depending upon the location of the switch, not location of the switch. Sorry, location of the inductor and our energy storing element. So these topologies, say these topologies, buck boost and buck boost topology are decided. So here you can see the limitation of this boost topology. So the moderate voltage can be achieved. Current is continuous. Efficiency is moderate at full load, and the output is of the single polarity. And the other limitations, large capacitor is required to reduce the output voltage ripple. So this is an interleave 4-phase boost DC-DC. converter. So here you can see 4 phase, just like 4 switches are there, 4 inductors are there, and 4 inductors are they have the separate magnetic core, and due to the phase shifting, the ripple current is shared in the ratio of the T by N ratio. So T is the switching period and is the number of phase. So the duty ratio, and N is the number of phase. And because of this, it means the all switches are not operating at a time. Okay, so they are phase they operate. Their operation is phase shifted depending upon the number of devices number of phase we are having. And so in this case, the reported literature, the efficiency comes out to 92% at a for a 30 kilowatt output, and there is a drop in the efficiency 8% because of the discontinuous current. Okay, so the continuity and a continuous and the discontinuous operation is important. Okay, so when this the drive is working as a convert in a motoring mode, the current must be continuous, and when this drive or the machine, the motor is working in a regenerative mode, so the current may be continuous or current may not be continuous. So that's why we have to decide which kind of converter we are going to use and what are the applications when we are using for only driving them for driving purpose, or both for driving as well as the braking purpose. You can see another topology with the resonant circuit. So duty ratio of this Q1 is greater than Q2, and because of Q2 enables the Q1 operate in a switching mode, reduction in size, and substantial gain be achieved in barrier. So this is a limitation. Bidirectionality cannot be achieved. So you have see this characteristic, and depending upon the characteristic, what kind of whether we are going to use say for retrieving the energy during braking. So this converter may not be say applicable. So this converter may be efficient, because it is working in a soft switching mode. Losses are less, and there is a reduction in the size of the heat sinks, or it is not required at all. Always DC-DC converter. This is the most popular topology. Okay, so just utilization of negative portion of the stress loop reduces the core saturation. It's important. When the core is saturated, so you have to make sure while designing a converter, core is not saturated. When there is a saturation of the core, it will draw large current, which is not desirable. It can provide galvanic isolation between input and output, and D must be more than 50% to protect the semiconductor device, and you can achieve the efficiency of 91.3. Yes, please tell me. Shall I? So shall I continue up to 10:30? Hello.
Sorry, I think unknowingly someone has unmuted. Please continue, sir.
Okay. So,
Thank you, sir.
and then clamping circuit, okay. So the clamping circuit are the active and passive required to resolve the peak voltage, peak voltage issue. So do you have some idea about the clamping circuit? What is the clamping circuit? I just give you the idea where the clamping circuits are required. Just see. Just see. Just see, these are two converters. One is flyback. This is forward converter. Say so. What is the basic difference between the flyback converter and the forward converter? In case of the forward converter, when you close the switch, when the gate is on, so the energy is directly transferred to the load. In this converter, flyback converter, when you close the switch, so initially the energy is stored in the inductor, and when you make this off, so the voltage across this side becomes double, and the idea is, which is not desirable, we have to limit this peak voltage. Okay, so in that case, during and when this is off, so the peak voltage may across the device while this transferring the power to the secondary side. So the main purpose is, we have to limit this peak voltage by connecting a suitable resistance. Okay, suitable resistances and limit the peak voltage or dissipate the extra power during the problem with the resistance and capacitance are there. So the problem with the circuit is, it dissipate the power. So as such, this is not desirable. So, and this happens in case of the flyback converter and the forward converter. So here the idea is, how to retrieve this energy when the switch is in. Okay, and in that case, active clamping is required. So I'm not going to discuss the acting clamp operation. So the acting clamp operation, we have an additional switch, and we operate this switch, either this switch or this switch, during this complete switching cycle, so as to transfer the energy to the load. So here you can make out the so you can go through the what is the active clamping, and you can make this what is the difference between the active clamping and the RCD clamping. This is RCD clamping. Just see, RCD. This is known as RCD clamping. RCD clamping, and this is applicable in case of the flyback converter as well as in the forward converter. And so you can just have a comparison of the RCD clamping and the active clamping. So in case of the RCD clamp, most of the leakage energy is dissipated as a heat. Hard switching related and power losses. Most difficult implementation of the self-driven synchronous rectifier with forward operation, and the voltage spike in Q1. EMI problems are there. Active clamping, most of the leakage energy is reclaimed Okay. So as such, and in case of the forward flyback converter, and when the switch is off, so that energy can be reclaimed, and zero voltage switching reduces the losses. Simple implementation, no voltage spike, and no voltage spike on the Q1 switch when it is turned off, and nearly lossless recovery. So this is the I have given you some idea what is the clamping, what is the resistance, RCT clamping, active clamping, why and which type of the converter need the clamping circuit. That you must go through. Okay. 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 So let me go ahead again. So let me finish quickly. This is another topology, Z zero voltage switching DC-DC converters. So here you can see the two converters. One is so the two converters are isolated. The complete isolation is there, and this topology based on the dual half this topology placed on the each side of the main transformer. So this is dual half dish. This is another dual half dish topology. Each switching device has a smaller private capacitor for switching. So this capacitor enables the soft switching, and this is not suitable more than 10 kilowatt capacity. And then there is another topology, sinusoidal amplitude high voltage bus converter. So this is the combination of the full bridge and the half bridge. Just say this is a full bridge and this is a half bridge, each side of a transformer, and not suitable for 3.5 kilowatt because of the complex sinusoidal amplitude control. So again, size of the limitation. Multi-port isolated DC-DC converters. So in that case, care will be calculation. Input ports are connected by isolated multi-winding transformer. Isolated multi is an input port. One is having battery and then supercapacitors. Each port is connected using interleaving techniques. Performance further improved by paralleling and phase shifting operation of this converter. And here it allows the bidirectional flow power through the generator braking. Okay, so this is important. And the auto transformer is required, which increases the weight of this topology. And here you can see multi-device interleaved DC-DC bidirectional converter. So you can say differentiate, you can make out difference in comparison to this topology, multi-port isolated topology, because here the transformer is not required. Okay. So let me discuss the other topologies, say for fast charging. So this is one common bus AC architecture, and which is having dedicated AC-DC conversion state. So this is AC dedicated AC-DC conversion stage with high frequency transformer. So this is a common AC bus, and we are having a different charging ports like 1, 2, 3, and so say one port, second port. There's so many ports are available there, and this is the combination of isolated DC-DC converter with a high frequency transformer, and this is an AC-AC converter, AC-DC converter. This AC-DC converter and isolated DC-DC converter with high frequency transformer. So we are going to discuss another common AC topology. So let me discuss AC DC stage. So this stage compatible 3-level 3-phase NPC, 3-phase bridgeless boost converter, 3-phase Wiener rectifier. Okay. So just in this topology, what are the advantage of this topology? Able to produce 5-level. This topology, 5-level can be produced, lower dB rating, low filtering requirement, and then problem is the imbalance power between the positive and the negative bus. Three-phase bridgeless boost converter. So this topology having an advantage of power factor correction, and it can apply or it can use different control strategies like SPWM, stresses current control, spectrum, voltage modulation, and with the each control technique, so the high power stress on the device is reported. 3-phase Wiener rectifier. This is similar to the 3-phase bridgeless boost converter. In operation, uses few usages, reduction in the losses, which minimize the losses of the reverse current, make it suitable for the fast charging. See, this topology is suitable for the fast charging because of this region, and controlled based on the high frequency. This controller, the controller work on the high frequency PWM, exhibits a neutral free connection, no serious commutation problem. So here you can the DC fast charger with the DC bus architecture. So initially we have discussed the fast chargers, but with AC bus architecture. This is AC bus architecture, and here we can use different kind of converters for AC. For DC bus charge, for DC bus architecture, is required again for the fast charging. So there is a grid, and there is central converter, and finally we are having constant bus, constant voltage DC bus, and there you can connect as many as converter or DC converter. Okay, number of DC converter depending upon the rating of the bus. So the DC bus voltage architecture of 600 volt, okay, and 550 amperes, and it can charge a vehicle within 10 minutes, and this charger are placed outside the electric vehicle. So normally DC charge are used for the fast charging purpose. Again, there may be two kinds of the bus. One is the unipolar and the bipolar bus. So there may be topologies which may be compatible to unipolar bus and the bipolar bus. So the this topology, 3-phase and bridgeless boost converter and 3-phase Wiener rectifier, they are compatible with the 2-level voltage source converter. Bipolar DC bus is compatible to following type of the converters. Bipolar sana, it has got three polarity: positive, negative, and zero. Unipolar topology, positive and negative terminals are there. So here you are having three terminals: positive, negative, and zero. So these topologies, given in the slides, are compatible to the bipolar DC bus. So the common architecture is AC/DC rectifier, input filter, DC/DC converter. AC/DC rectifier is used to regulate the power factor. Okay, and create a common DC bus voltage for all DC converters, and the input filter to reduce the harmonic content. Okay, so here we are talking about this topology, AC/DC. So let me come to the DC/DC stage. So here this is the DC/DC stage. So in case of the DC/DC stage, you can use the different topologies: multiple interleaved buck converter, full bridge LLC resonant converter, phase shift full bridge 3 level 3-phase inverter. No, this is something different. DC/DC stage. Here the DC/DC stage. Multiple interleaved bus converter. Okay, and so this is the data given. You can go through this. I will provide the slide. You can go through this slide and just and the full bridge LLC resonant converter. So there are advantages. And these are the advantages and these are limitations of this topology. Phase shift full bridge converter and suitable for high power applications. Short switching possible, control is simple, low current stress on the devices. And they are having some drawbacks like a high circulating current in the freewheeling interval and high voltage stress on the rectifier. Some limitations. So we have to look for that. So as say for given load, the devices are not overloaded. And here now lastly I would like to conclude what are the emerging switch topologies for converter. So simply you can go through this right up. Switching circuits for DC/DC converter topology, or electric vehicles they are supported by SI based semiconductors like SI based MOSFET and SI based IGBTs. So they are having limitations of carrying high current with respect to the size, and it is expected that in the near future wide bandgap silicon topologies, silicon devices, not topologies, devices. And there are the two categories. One is silicon carbide. There is other this kind of devices, gallium nitride. So that may replace the ISI based semiconductors in any future for higher power applications in this automotive industries and why why this device wide bandgap semiconductor devices are suitable, because they have a higher bandgap, large critical breakup, large critical breakdown electrical field, higher thermal conductivity, large electron velocity, and lower dielectric constant. So as such, now the people are working on the devices, wide band gap silicon devices, wide band gap silicon devices. So as we have already discussed the SI based semiconductors. So the limitation is the size for high power rating. So these are the limitations. And here you can see now they can be operated up to 5 gigahertz frequency. That's why the size becomes smaller. Again, there may be issues say like at higher switching frequency, losses may be high. Okay, that you have to keep in the mind. And they can with this this is surprising, they can withstand a temperature of 300 centigrade 300 centigrade in comparison to SI. High power resources and more compact size, smaller sized sink is required. Size sink is required. High frequency allows the reduction in the size and the passive component. Because of the higher switching frequency, there is a reduction in the size of the passive component, and their design is less costly. Okay. And this is regarding summary of say DC-DC converter for BEV powertrains. I'm not going to discuss this the complete. So we have to see how they are differing in the nature. What are the advantages? What are the problems? So each type of converters they are given. Okay. So what can I conclude from this from these discussions? This type of topologies are suitable for electric vehicles or the plug-in vehicles. So let me have a look whatsoever we have discussed, and what can I say? Say in case of the fast charging fast chargers topologies. So the wideband silicon devices are recommended. Why they are recommended? Because of because when we are going to recommend any topology, so we have to look at the different features like losses, effectiveness, cost, reliability, and so on. And it can be concluded, so we can say you can go through another when we are going to integrate two or more energy sources. So the MDIBC topology is recommended. MDIBC topology is recommended. For when two or more than two sources to be integrated. So what is the full form of MDIBC? Multi-devices interleaved and boost converters. Interleaved DC-DC bidirectional converter. Okay, so this can be used for it when the converter is placed inside the vehicle, and that is for the BEV or PHEV powertrains. Okay, that will be the best option. So in case of a fast charger, Vienna rectifier topology may be recommended. So in case that is in case of AC DC stage. And in case of DC stage, say for fast charger, Vienna rectifier is recommended for AC DC stage, and for DC stage multiple interleaved buck converter topology. Multiple interleaved buck topology is recommended. because why? Because why topology required? We have to charge, because our DC buses are at high voltage and the battery is low voltage. That is why such topology is recommended. And finally, WPGS or the band gap silicon technologies for power converters may play a significant role in order to reduce, or I must say, or to improve the power density. Okay, and say, let me tell you the reference from where I have taken. And suppose people who have attended the course on the DC-DC converters or the switch mode devices, so they may be aware of all the topologies whatsoever we have discussed. So I have refer this info. I have taken this information from a topic DC converter topologies for electric vehicles. And fast charging stations. State of art and future. And suppose somebody want to do research or PhD in this area, so what he can do, he can go this paper, and there are the other references which are available in this paper, and then one can decide the future course of action which is, say in which area is going to do the research. And okay, so this is all for today. So this is all for today. So any queries or something like that? Any queries from your side? Please tell me. Hello.
Sir, we are able to hear. The participants can interact with the Prof. If you have any queries.
Yes. Sir, good morning, sir.
Good morning.
I'm Shantosh. I'm Shantosh, sir. I have few doubts, sir. Can we
Yes.
use a non-isolated jet source converter for electric vehicle applications, sir?
Non-isolated.
Yes, sir.
And for high power application, we go for non-isolated.
For high power applications.
For high power applications, and as such, what is that? Say the isolated say topologies are recommended for the low power applications. Say for fast charging. Say for say what do you call it? Say for suppose you want to charge say at a low level. Say you want to charge the battery say up to 10-20%. Say for time being for low power applications. So the basically what say how the topology are say the classified. One is the isolated and then is the non-isolated. So the isolated topologies are recommended non-isolated. So the non-isolated topology are recommended for say low power applications. And high power application we prefer the isolated topology. And as such there is ease of control.
Sir, for, you recommended one book, no, sir, Abraham Press book. So can I use that control logic for fifth order system? Because my system is fifth order system.
So as such I recommended say one book say by I will tell you the name, Abraham Pressman.
Yes, sir.
So this is
Yes, sir.
available as such. This is a conventional book. This is a very old book, conventional. And they did discuss about the design of the PI controller. So they have given the basics. So initially you have to understand the basics. Why there must be chapter 8 or 10. Why the stability issues are there.
Sir.
And until unless you don't appreciate the stability issues, and then how you can go further for the improvement of the same such controllers. Nowadays our fuzzy controllers are using and so forth. Say for simulation purpose fuzzy controllers, everything is okay. So the problem comes in when you are going to realize and implement the converter
Yes, sir.
for a commercial use. Okay, so your design must be very simple, and everybody must be able to understand.
Sir, another one, sir. If any system has complex conjugate zeros in the system, so how we can stabilize the system, sir? Any method? Generally, 1 0 in the right hand side of just right side of S-plane, then we can do some control techniques. If complex conjugate zeros on the right half of the S-plane, then what we have to do?
We have to design a compensator. We have to substitute those,
Yes, sir.
whatever it is, shift those, say ऐसा say zeros on the right hand because of stability issues are there because of the RHP zeros, so we have to design
Yes,
a compensator, like we have to design a compensator.
Lead compensator or lag compensator.
As such, both as such, here we talk about the both lead and lag compensator.
Can we use PI
As
plus
such,
lead compensator?
we have to design a compensator lead or lag. What do you mean by the lead and lag compensator? So
Yes.
a compensator which operates like a lead compensator or lag compensator depending upon the phase, the frequency, depending upon the frequency. As such, I can tell you just see. So when we design a compensator, so the total loop maybe you can go through maybe like this, say these are the two, the pole and zero frequency. So this is zero frequency, this is a pole frequency, and again maybe like this, and there is bandwidth for which gain is constant, and lower frequency the gain must increase, and beyond at a higher frequency the gain must decrease. Okay, so that is how you can stabilize your system with this complete frequency range. Okay, and depending upon the pole and zero frequency, we decide the bandwidth of the controller. So here you can say this must be working as a lead compensator, the same compensator depending on the, and here this will be working as a lag compensator. So have you studied the operation of the governor? A mechanical governor. How we operate the mechanical governor? Okay. So when the disturbances are low and you want to share the more power, increase the gain. Okay, and when the disturbances are low, low disturbance, increase the gain. Higher disturbance, decrease the gain. So this is most such this behavior is just like that mechanical governor. How we adjust the gain. So this is the gain of the compensated. This is a gain curve of the compensated system. So that is how you can say, stabilize your system.
Yes, sir. Thank you, sir. Sir, how much bandwidth?
Yes, you can go through that book, and there is another book I will let you know that I am not able to recall the name of that book. So the different techniques are available just to say to stabilize the second order, third order, and the fourth order system, and by pole placement. Okay.
Okay.
So as such, you have to whatever you are saying, you have to nullify, you have to nullify those zeros and.
So generally, how much bandwidth we have to consider? High bandwidth we have to design converters.
High bandwidth, normally, as a high bandwidth is decided by the frequency range.
Yes, crossover frequency. Yes.
Crossover frequency, So as such, we have to decide this frequency range.
Usually, how much bandwidth they will take? Usually, how much bandwidth they will take, sir?
How much?
In terms of crossover frequency.
As such, this is a crossover frequency. Just this is a crossover frequency, and just we select the zero frequency and the pole frequency around the crossover frequency. Okay, and how much it must be there. So normally, when we talk about the switching frequency of the converter, this must be 20%. The crossover frequency, the crossover frequency must be 20% of the switching frequency.
Okay, sir.
That is the criteria.
Yes, sir. Thank you, sir. Thank you very much, sir. It is very
The crossover frequency must be 20% of the switching over frequency.
Thank you.
Okay.
Thank you, sir.
And then you decide the pole and zero frequency, and then you decide the pole and zero frequency. So that will decide the bandwidth. Okay.
Thank you,
so
sir.
this must be there must be some range, otherwise there is some disturbance here, so that here and there the system may be unstable. Okay, listen.
Thank you, sir.
Welcome. Okay, so
Sir, I think there are no more queries, sir. Thank you, sir. Thank you.
No, sir, good morning, sir.
Good morning. Good morning.
Sir, how are you, sir?
I'm fine.
Thank you.
Then,
sir, thank you, sir, for your nice lecture. And so you actually accepted the invitation all of a sudden. So even in the busy schedule also.
as such, I'm not now. I'm not at Rourkela. I am at Jaipur.
Okay, where you are, sir, now?
I am at Jaipur. So that's why I couldn't prepare this topic very nicely. Maybe some problem may be there. Otherwise, I try to provide all the whatever the information state of art is available with the converters that may be suitable for the battery vehicle applications. Okay.
Thank you, sir. Thank you so much, sir.
Well,
thank you, sir. Thank you so much.
Lecture and giving many inputs for the yes.
Thank you, sir. Thank you for joining with us.
welcome. Okay. Shall I take your leave?
Yes, sir. Please, sir. You can.
Yes, sir. Please.
Thank you. Thank you.